Welcome to this other edition of our numerical method class. I hope you enjoy your sleep, you rested well, and you also went through the notes, and you are well prepared for today's session. I hope so. I will not ask anybody if you read your notes. I hope you don't be scared. I will not call your name. So I say I hope. So if you didn't do that, do that next time. Do that next time, so that when I will ask, have you read? Have you prepared? You will not be embarrassed, right? So this is a grace period that I'm giving to you. Okay, so what did we do yesterday? Of course, yesterday we covered the Simpson's trapezoidal rule. I mean, I say even trapezoidal. The composite Simpson rule, because previously it was the composite trapezoidal rule, and yesterday we derived. So we went through all the steps so that when you see the formula, it will not appear as if an angel or somebody just appeared and said, take the formula, and you just swallow it. No, it's bitter for me to swallow. I don't even understand the formula. No excuse, because you saw how the formula was derived, right? So there will be no excuse. Next time you will not say, oh, I don't understand this formula. I don't even know where it comes from. Me, I come from Bamboland, but this formula, I don't know where it's coming from. You all derive the formula, so you know where it's coming from. Okay, so let us look at the formula again. Let us look at that formula once again. I'm going to share. I'm going to share the screen. Okay, so this is what we found, right? So we use the original Simpson rule, which is defined over two sub-intervals, because we said that we need an even number of sub-intervals in order to apply our Simpson rule. So here on the right, we have our original Simpson's rule, right, for two sub-intervals. That is, we integrate from x0 to x2. So we have two sub-intervals. And you have three evaluations of the function. The first one is at x0, then x1, x2, which are denoted here by f sub 0, f sub 1, f sub 2. So that's what we have for this basics Simpson's rule. Now for the composite, obviously we will partition our interval, but the number of sub-intervals should be even, right? So that we can take two consecutive sub-intervals to define the rule. So that's the reason. Always bear in mind that when you apply Simpson rule, the number of sub-intervals has to be even. So we can write that as 2 times n, where 2n is the total number and n is half the number of sub-intervals. And in the summation, as you can see here, this n is not the total, but it is half this, because this sub-interval has, I mean, when you integrate from x sub 2k minus 1 to x sub 2k, there are already two sub-intervals here. So if there are two sub-intervals, 2 times this n, it will give you the total 2n. I hope you understand this. It's not witchcraft, my dear student. I wanted to say my dear friend. You are not my friend. My dear student. I hope you understand this thing. Hmm? Or you want me to speak Oshibambo? I hope you understand this. This is the total number of subinterval, 2n. And you have here, we sum from 1 to n. Because this integral has 2 subintervals. So in total, we have 2n. Is that clear, my student? Is it clear? This n times the 2 subinterval here will give a total of 2n. So when you take the summation here, never make the mistake to take 2n here. It is half the total number of subintervals. All right. So now we apply our Simpson rule, our composite Simpson rule. We apply Simpson rule to this subinterval with the summation in front. So this is our basic rule. We use that basic rule, we substitute there. So you can see that in this subinterval, we have 3 points, x sub 2k minus 2. The middle point will be 2k minus 1, and the other end point will be x 2k. And that is exactly what I represented. I represented here. You can see it here. Here. If you are not satisfied, I can even represent like this. That interval, we have this. We have the third point there, and we finally have this. So this is the point, right? This is the interval, right? Here we have x sub 2k minus 2, x sub 2k minus 1, and finally x. So that's what we have. We have these 3 points. So when we compute these integrals, you see that we'll be getting evaluation at those points. Now, if you expand this summation, as I explained yesterday, right, there are points that will be repeated. The inner point, I mean, when I say the inner point, for the subinterval, when I say subinterval, there are 2 subintervals, right? When I take an integral, if you want, an integral, in an integral, you have 2 subintervals, and the midpoint of the 2 subintervals are the point that I denoted by x1, x3, x5, x7. So you see that the subscript of those points are odd. So this odd point will not be repeated. They will only be evaluated once throughout. But now the remaining point, except the end points, that is x0 and x2n, the remaining point, those with even subscript will be evaluated twice, in such a way that when you add them up, it will be 2 times those values. So when we expand this, we take that into account and group them accordingly. Right? So that's what we have here. So we take the first point, the last point, which we group here, and then the remaining one, we look at point with odd subscript. Those ones will not be repeated twice. We also group them separately. So these are the points, this one. I say odd, right? Yeah, this one. And because the midpoint, which had an odd subscript, has a factor of 4, that factor of 4 will multiply the h by 3, so it will be 4h by 3. And that's what we have here, 4h by 3. Now the remaining terms, those with even subscript, will be summed twice, so it will be 2 times h by 3. So the factor will be 2 times h by 3. Now, if you want to have a formula similar to the one on the slide, it's similar. Just take this last position and put it in the middle. It's exactly the same. So, and that is it. So that's what we did yesterday, right? That's what we did yesterday. So today we are going to apply it to a particular example. Okay, so we can rewrite our S for Simpson, right? Obviously, this is a composite, composite Simpson. Okay, now you see that here we put equal because this is the definition of S. That's why we put equal. This is the rule. We put equal. But if you write integral, we say integral is approximated, then we write approximation. But if you define the rule, you write equal. Okay, so we have this one, h by 3 into f of A plus f of B plus, we can take this one if you want. We can change the position. It doesn't matter. The result is still the same. 2h by 3, right? Summation. So the factor of 2 is for, as we saw, for even subscript. Even when you have the 2 there. Now, and for that one, we sum from 1 to n minus 1. Because one of them has already been substituted in the first result here, f of b. It's already there. So that's why we sum to that. And here we have f sub, which I can write x of 2k. So this is the even, right? Now, plus for the earth, it will be 4h by 3. Of course, that 4 comes from the original Simpson rule, right? The value in the middle has a factor of 4. So that same factor is here, the 4. And then we have the summation k running from 1 up the way to n. So you take the entire summation, right? F x sub 2k minus 1. So that is our rule. Another way, right? Another way to make this simple, we can just say, you can rewrite this by saying that this is equal. This one, there's no problem. Group the first and the last term. Right? Now you can say plus 2h by 3. Now you just say summation. Here you say summation on even. Right? Egg and here you have even term here. Or you can say k even, right? Even k even if you want. You can write e here for even to say that you sum all of the even, right? Plus 4h by 3, and then you sum here over the odd. F x sub O to indicate odd. So if you write this, it's still correct. Why? Because you just look at your subdivision. the partition, the point in the partition, you group them. You take the 0 and the n, the two n, that is the first and the last point, group them here, and then the remaining you will group into odd and even, and you just sum over those ones. That one is even much more easy, right? It's much easier to use this one, because to remember all those things, yeah, you can still do that, but what I want to say is that it's easier for you if you just say we'll be summing over the even subscript and the odd subscript. Then you will not care about the limits, right? Because if you already extracted f of a and f of b, the remaining things will arrange themselves. Okay, now let us look at an example where we are going to apply this, and you will appreciate this comment or this remark. Good. Now, example, let us look at an example. Oh, okay, let me. I will share a new slide. Share a new slide with you where we take an example. Or let me do this instead of sharing the slide. Right? That is, instead of toggling from one screen to the other one, I mean, take sometimes some delay. Let me just copy that the example from the notes and write it there for you, so that I will avoid toggling from one screen to the next. Okay, so let me do this. Example. Okay, so I will copy that example for you, right, to make it simple. So we consider the following function. F of x equal to 2 plus sine 2 square root of x. So that's our function, f of x. Right. Okay. Now you're asked to use Simpson rule with 11 sample points. Be careful, be careful, be careful in the statement. You say you use 11 sample points to compute an approximation to the integral of the function f over the interval 1, 6. Okay, so let me write it here on the slide. So example. Right. So we consider the function f of x equal to 2 plus the sine of 2 square root of x. So that is our f of x. So you're asked to use 11 sample point right to compute an approximation of okay, now 11 sample point, you can see here we have 11 sample point. Right. And if you recall, we said that for the trapezoidal rule, we need an even number of what? We can recall, we need an even number of what? I mentioned even numbers when it comes to the trapezoidal, the Simpson rule. Camilo, tell us which, what did I say in terms of even number of something? What was it? Number of what? When I say that for the trapezoidal rule, we need an even number of something. What was that thing? Because here we are given 11 sample points. Is it possible for us to compute or to use the Simpson rule? Is it possible? Here we have 11 sample points. And I want you to participate. It shows if you are paying attention, if you are participating or not.
Sir?
Yeah.
The subintervals must be even.
Okay, subinterval, very good. The number of subinterval has to be even. Now we are given 11 sample points. Does that violate the fact that we need an even number of subinterval?
Yes, sir, it does.
It does violate. The statement mentioned 11 sample points. What does it violate? Okay, let's say I have 3 sample points. How many subintervals would 3 sample points define? I have 1, 2, 3. These are the sample points. How many subintervals do I have if I have 3 sample points?
2, sir.
2 subintervals. Now, if I have 11 sample points, how many subintervals do I have?
10.
10 subintervals. Is 10 even? Yes, 10 is even.
Yes.
So it doesn't violate. So you see that the number of subintervals, if I have a certain number of subintervals, to obtain the number of points over the entire interval will be the number of subinterval plus 1. So if I have an even number of subintervals, the number of sample points will be odd, right? So it doesn't violate. So you have to be careful about the statement. You say 11 is not the number of subinterval, but it's the number of sample points. The point, if you count 1, 2, 3, all the points of the partition is 11. If it is 11, it means that the number of subinterval will be the number of sample points minus 1. So if I have 2, you see 1, 2, I have 1 subinterval. So the number of subinterval plus 1 gives the number of points, or the number of points minus 1 gives the number of subinterval. Great. So everything is in place. There's no contradiction here, right? So which means that 11 minus 1, which is 10, is the total number of subinterval, which is an even number. So we will say that 10 is equal to 2 times n, because we need that n in our summation, right? If you want to use the formula. All right, because in the formula we need n, not the total. Total by 2, which is n, that n. I mentioned it already. So you have to be very careful when it comes to this statement. So 11 sample point implies that we have 10 sub-intervals. 10. So in our formula, you agree with me that n is 5 if you want to use the formula. Right. But I say that if I have that, okay, we know that they're equally spaced, so we can compute h. So h is what? B minus a by 2n, which is 10. So that will be 5. We can 6 minus, okay, let me write. 6 minus 1 by 10, which is 0.5, right? Because this will be 5 by 10, which is 1 by 2, which is 0.5. So in other words, if I want to know all the points, obviously I can write already that xk, if you want, it is the first point, which is 1, plus kh, right? So, and we know that k in total so we go to 10, right? Because we have 11 in total, right? So I can write all those points here and group them, right? I can write and group them. If I don't want to use the formula, because I can easily do that, I can always do that, right? I say I take A, B, because we know already that A is 1, B is 6. So I have these 2 points, which I will group. If you look at the formula here, I have f of A, f of B. These are the 2 points already here. Then I will need the even and the odd, right? If you don't want to use the formula, this is another way to see. So now I have this 2 points for the first one. Now, if you want to look at the number of even, this one. So you agree with me that if you look at the even, we will get what? Because we say that these are the subscript here. So for the even, I will have x 2, right? x2, x4, x6, x8, and x10 is already here. This is b, right? So these are the even. And now for the odd, I will take x1 here. x1, 3, 5, 7, 9. So you see that this one is the last one when k is equal to n minus 1, right? Because we multiply by 2, it will be 2n minus 1. Anyway, 2n minus 1 will be this one, which is 9. So you see that we have grouped all of them. You have x0, x10. Now you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the odd. And you substitute in the formula. So therefore, we can say that our composite Simpson rule for this case H is our 0.5. So that will be equal to H by 3, H by 3, which is 0.5 divided by 3. Then we have F of 1 plus F of 6 plus, now we know that for even, it is 2H by 3 or H, okay. So that will be 1 here. 2 times 0.5 is 1. That's what 1 by 3, which is 0.333. Okay. Now here we have F of what? F of these 4 terms, right? Because we say odd, even, this one. So F of x2. But what is x2? Okay, so if I write the general formula here, so I can write here that xk is equal to 1 plus 0.5 into k. Right, so that's what we have. Okay, and this in the formula, if you recall, in the formula, we say x sub 2k. Now, if we say 2k, this will be 1, right? So let me write it directly here. So for this will be 1 plus k. All right, so now with this one, if I say F2, we know that F2 will be 2. All right. Because to say X2, I need K to be 1. Look at this one, X sub 2K. To get 2, I let K to be 1. I put 1 here, 1 plus 1 is 2. So F2, which is this one, is 2. Plus, because we are summing all this, now for 4 here, K has to be 2, so that will be 3. All right. Now for 6, if I want 6, K is 3, then it will be 4. And finally, for 8, this will be 5. So we have 2, 3, 4, 5. We just increment by 1. So that will be the value of the function at those points. And finally, the last one, this one, that will be 4h by 3. So 4h will be 1, 4h will be 2. So this will be 2 by 3 into f of, here we have 4 here, here we have 5 terms. Okay, so okay, now I can do something similar here. If I want to write x to k minus 1, right? Now, if I substitute 2k minus 1 here, obviously, okay, 2k minus 1. So if I multiply that by k, anyway, it doesn't give us something beautiful. Okay, the formula is not nice like the other one. But anyway, let's multiply that. So if you multiply, it will give us, it's not too nice. But anyway, all right, 2k minus 1, let us expand that 2k minus 1. So here we have 2k minus 1 times 0.5. Okay, so that will be 1 plus, I'll keep this, that I'll write it as 1 by 2 like this, and then you have 2k minus 1, right? This one, that's exactly what we have. I want to write it in a simple way. Now, you see, this will multiply that, it becomes 2, so that will be 1/2 of what? 2. Now expand, minus 1 plus 2k, right? You agree with me that this is what we have? So this is 1. And this is 1 also. Oh, what I say? Because, oh, no, that's not 1. I took k as if k was 0.5. 0.5, I already substituted. Okay. So this is what we have in total. So this will be 2k. So this is 2k plus 1, right? By 2. So it is 1/2 of 2k plus 1. Good. So we can check now. When k, okay, for us to get 1, x1. So for x1, we need k to be 1, right? Okay, I don't need to explain. Okay, so what I'm saying, to get the value here for x1, k is equal to 1. So if k is equal to 1, to get 1 here in the subscript, I want this to be 1. So what should be the value of k? K should be equal to 1. If I substitute k equal to 1, the subscript will be what? It will be 1, because it will be 2 minus 1, which is 1. So I come into this, because this is the expression of x sub 2k minus 1. This is the expression. So I just take, in this formula, k equal to 1. So if k is equal to 1, this is 3 by 2, which is 1.5. So I can write here 1.5, right? Okay. But remember that we will skip that by 1. So the next one will be 2.5. Right? I'm just writing it for you, but I will explain. Then the next will be 3.5 plus, you can even see from this one, right? 2.5, 3.5, 4.5. That's 4.5, right? Then after 4.5, we have 5, which is this one, and we have 6. That is, we have the total of 1, 2, 3, 4, 5. 1, 2, 3, 4. Wait. 1, 2, 3, 4, 5. We still need another one. 5.5 plus f of 5.5, and we close. Because the next one is 6. Okay, so we are done. So those are the points. You can just substitute in the formula and you are done. Right. So I don't know if this is long. It depends on what you find easy, right? The one that is easier for you. Either you use your formula, you substitute, or you group. Because what I did here, I just grouped the terms, the even and the odd. You group them, and then you compute, you substitute in your formula, and that is it. Since we know already what is the value of f, you just compute f of each of these points, right? And you are done, right? You use your calculator because you know already the values of each x, and you just substitute. Okay, because of these 2, you see that 2 with a common factor to all of these. You have 2 here, you have, so you can factor by 2 here, then it will be 2 here as a factor, then the rest will be 1 plus 1 plus 1 plus 1 plus 1 plus. Or still, no, sorry. You cannot factor because It's only here, right? You cannot, sorry. But you can group all of them, yeah? Because each time you have 2 plus 2 plus 2 plus 2. So you would group the 2. Okay, let me write what I mean here. Okay, so what I'm trying to say, okay, what I'm trying to say, to make your computation easy, or easier, you can write that summation is this one, right? So we have 0.5 here, or this is 1 by 6, right? Because 0.5 is 1 by 2, so this factor will be 1 by 6. Okay, now this sum, we have 2 plus 2 plus 10, this will be 4 plus, now we will use sine of square root of 1, which is 1, right? Plus sine square root of 6, so that is x, right? Oh, 2, there's 2 in front. So you see that this 2 plus, because I'm adding this 2 and the other 2 before. So I need to put 2 in front. I missed that one. So there's a 2 here in front. And there is another 2 here. Good. So, and that is it for this term. Now, plus, now for this we have 1, 2, 3, 4 terms, and 2 times 4 is 8. So I can group that here. So I will have 8 here in front, then plus sine 2 square root of the argument, which is this one 2, plus sine 2 square root of 3, plus sine 2 square root of 4, plus sine 2 square root of 5. And then I close. Okay, I will just indicate that it comes from the previous. Yeah. Now, for the last one, 2 by 3. Similarly, I count the number of 2, because remember that there is a 2 that will be added each time. 1, 2, 3, 4, 5. 5 times 2, 10. So there will be a 10 here in front, plus sine 2 square root of 1.5, plus sine 2 square root of 2.5, plus sine 2 square root of 3.5, plus sine 2 square root of 4.5, plus the last term, sine 2 5.5. Okay, so that is it. You have you take your calculator, you compute this, And never forget to set the mode of your calculator to radian. Each time you deal with trigonometric function, always set your calculator to radian. I will not mention that enough. Okay, so what happens? So if you compute all this, what do you get? The value that you obtain will be 8.1830150. So the computation of this will give you 8.18. So make sure that you obtain the same value. 1.550. All right, so this is what you will obtain. So please make sure that your computations are correct. Okay, let's take the last remaining 10 minutes, right? And let's see if we can use our Python program to code this. Okay, let me see. Let me see. Let me try to. Okay, because I think we have spent some time without even programming. And I will not say it enough. You need to program regularly. The way you eat mahangu regularly, you need also to program regularly. Am I right, Kashupi?
Say I don't know.
How come you don't know? You should know. You see that you are unjust. You don't want to tell the truth.
Say today is not the time to tell the truth.
Sorry?
Say today is not the day to tell the truth.
What? So today is the day to lie. To lie.
No.
If you don't tell the truth, what should you tell?
Nothing. No, not even a lie.
Oh, triple shame. Triple shame. All right. Okay. I'm opening. I launched the Jupyter Notebook, which you all have, I'm sure. For those of you who have laptops, laptops, no laptops. For those of you who have laptops, you should have this program installed. During the first semester, no, that was no. During the first semester, was it during the first semester? Yeah, during the first semester when we had our face-to-face class. During the face-to-face classes here in the lab, G39. So you remember that you were using this Anaconda package, right? Anyway, if you don't remember, I advise you to go to Anaconda, or you Google Anaconda. Okay, if there's time, we will do that together, right? Maybe not today because we don't have enough time. For those of you who are not aware of it, I'll have to repeat it. Okay, but for now, let me do this. For now, let me open. open this. We are going to program this exact function. I mean, we are going to perform this computation. Do you have a class after this?
Yes, sir.
At what time?
9:30.
Oh, so we only have 6 minutes. Okay, what I would do, we will stop, but what I would do, I will proceed so that later on, you can watch the video and see the programming aspect, because I want to add that part. It's an extra, it's not necessary, but it's useful. When I say it's not necessary, it's useful. It's useful. Okay, but let me share the screen already with you, so that when it will be 27 or something like that, we can. I will ask you to leave, né? But I will continue because I'm recording. Or you want me to also stop the recording? I'm asking you a question. That question is so simple.
I can watch the recording, sir. It's fine.
Oh, okay, good. All right, now let me share the screen with you. Jupiter, notebook. Okay, it's this one. Let me see. Great. Ha ha ha. Oh, guys, not witchcraft. Oh. Okay, so this is our. You can see, huh? Do you see what I see? What do you see on your screen? Hmm? Do you see something like me? Hmm?
So I can see Jupyter Notebook.
Great, 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 great. You should also have it. You should download it if you don't have already.
I have it.
Oh, that's great. That's great. Yeah, interesting. All right. All right. Okay, do you recall how we define the lambda function? Do you recall? Hmm? I'm asking you a question. You remember that last semester we defined lambda function. We can define the lambda function here. Do you remember?
Sir, last semester I didn't have numerical methods.
Sorry?
Last semester I didn't have numerical method.
I'm not only talking to you, I'm talking to the class.
So the class is not answering, not the responding.
Okay, class. Oh, class, say something. Oh, guys, say something at least. Say something. Hmm? Oh, you don't want to say something? Hmm? You don't want to say something? Okay, now our function is 2 plus sine. Okay, for sine, sine, is it in math or is it in numpy? Okay, let's try with numpy. Yeah, it should be numpy also. Then we use our sine function because it is in numpy. Right. Okay, so that's how we. So that's what we will use, right? So f is our lambda function. What else do we need? Okay, we need the partition of the interval. We say that our interval, we take capital N to be 20. No, sorry. To be 10 times 5, right? And then we can compute our x. Oh, it's already 29. Okay, please, for those of you who have a class after this one, you can leave, right? You can leave. The others, those who want to watch, can stay. We are going to write the program. Thank you for your kind attention for the other student. See you when? On Friday, because tomorrow we don't have a class, right? Thank you so much for your kind attention. And those who will stay, you can stay until I finish this example, and then that will be the end. Thank you. All right, now for those who will stay, I will proceed. I will proceed with the computation, right? So for our Simpson rule, we need all the x sub k's, right? So there are many ways I can compute all the x sub k's. I can define x to be x. Anyway, it depends. I can define x, or I can just leave, because we need the subscript of each of the x. Okay, so I can just use x to be... Okay, let me do that. So I can say x is equal to, then I use the NumPy array to make it a vector or an array. I will be able to access using the subscript, right? So NumPy array, good. Now, since I know all the points, there are 10 in total, so I start from 6, right? So I can start from 6, no, sorry, from 1 to 6. So that we have 1, comma, 1.5, because the step h is 5, right? I'm just doing it manually, right? And then 2, comma 2.5, 2.5, comma 3, sorry, 3.5, comma 4, comma 4.5, comma 5, comma 5.5, comma 6. Right, okay. But because I want this to be, okay, since I already say array, I can put a dot there to convert everything into real numbers instead of integers. It doesn't matter, but it will still do that automatically, because I can still add the dot at the end. Okay, so this is our x. So all the values of x are there. I enter. So I have, okay, so that is it. So I have all these points. I can also say that n, so that is capital N. So small n, or lowercase n, is 5, right? Obviously, you should be aware of this. If I have a list like that, the first value will be assigned the first value to the right, right? And the second, that is n, will take the value 5, and capital N will take the value 10. Right? I just okay, and then I can write my rule now, the Simpson rule. I can use a loop if I want, right? Because it's a summation. Okay, we can do that. We can use a summation. So what I would do, I will write a sum, right? So I can first compute the, yeah, I can take the sum. I can take the sum on the odd and the sum on the even. So it's up to me. There are many possibilities I can write this program, right? Because if you remember the formula, we have two sums in the formula. So I can also write two sums, and the first sum, okay, so let me do this. I will call this, the first one, I will call it S. So for the odd, I initialize that to 0. And the other one is the sum for the even, like that. Okay, so we start with the, okay, let's start with the even and then the odd. Right. Anyway, that order does not matter. So equal. So I initialize each one to 0. 0.0, comma 0.0. Right, and now we use the loop, right? We use the loop. If you recall, in our numerical class, we said that if you want to define the loop, in the summation, we initialize that first to 0, right? We initialize that to 0, and we perform the loop. Okay, now for the loop, I will write the for loop that is for A in range, right? In range. Okay, now which range do we have? We take the range of n, right? Because the range of n. And we can always correct that. So we take k in the range of n, meaning that k will take the value 0. Okay, because we don't want to put 0 there, I would just take 1, comma. So if I say in the range of n, it will take from 1 to n minus 1. So if I want from n to n, I can say the range of n plus 1, right? Because that is for even, and we know that for even, it will take all from 1 to n. That is correct already. Okay, now into SE, I will assign SE, which is initially 0, plus, okay, now what do we want? We want to evaluate the function f, that function, f at what? At x, right? X what? 2k. You remember now, because this is odd. So that will be 2k. Right, if I do this, I'm done with all the odd, right? We'll be summing all of them. Because we go to up to n, then to n. Okay, now when I say to n, anyway, in this case, because 2n will be included, I could have taken, right? You see that here you have to be careful. Either we group everything, we compute that summation once, that is the trapezoidal rule. But if we want to use our formula where we group f of A, f of B separately, then you have to be very careful in the formula that I'm writing, because if I put 2k like this, the last value here, then I can remove this. So if I remove, the last will be n minus 1, which will be 2k minus 2. 2k minus 2. Then this is correct at this stage. So I can write all this, right? So at the end, let's see. And now the second one, I will have another for loop, k in range. So we do something similar for the range. Now I will take from 1 to what? Because we want to reach to 2n minus 1. 2n minus 1. But let's see. Yeah? So I enter. Now I will copy this because it's similar. I copy and then I paste it there. I just change E to O. Alt. Alt. Now here I will put 2K minus 1. Right, because it has to be odd. Now, let's see what will happen when K is equal to 1, we have 1. Now, the last one will be when K, okay, then I can go to plus 1 here. If you want, if I say plus 1, it will stop to 1, to N. So the last value of K here will be N. So if I take N here and substitute there, it will be 2N minus 1, good, which is good. And here will be 2N minus 2, 2N minus 1, good. Great. So you always check, eh? It's not witchcraft, you check. Okay, so finally the final S will be what? Will be our H. H is 0.5, eh? H is 0.5. So what we could have also done here, let us write the limit of the integration. You say A, comma B, comma. So A is 1, B is 6. I think it's that one. From 1 to 6. Yeah, that's what we did. We integrated from 1 to 6. So we have A, B. So we can also define H. So if we define H here, we say H is equal to E minus A divided by capital N. Capital N being 10. Great, so that is it. So we have it here. So I can use H by 2 here, H by 3, yeah? H by 3. So I can say this is H by 3, right, into F of A plus F of B. Good. Now plus SR. So with this one, I should get the result, right? Okay, so we are going to print the result, print, to see if give us the value 8.13 whatsoever, that value. If it doesn't give us that value, it means that something is wrong in our program, and we will check, right? That's how we do programming, right? In the first go, there might be error, then you check to fix where the problem is. So let's run the program. Okay, so we are running the program. Let's see. But it's taking time. It shouldn't. Oh, no. You see, the value here is 17. So it means that there's something we did not do right. And we need to check, right? It shouldn't be 17, it should be 8. Okay, what did we do wrong? The limit of integration is from 1 to 6, right? Let's make sure that is correct. The limit of integration is from, 1 to 6. So A is 1, B is 6, capital N. Number of subdivision is 10. And N itself is 5 because it's divided by 2. So N is 5. Okay, that one is correct. Now, the lambda function F is 2 plus, oh, you see, there's an error here. The lambda function is not correct. It's 2 square root. 2 times square root. Yeah, I was already wondering that, but how come everything, when we substituted, everything was fine? All right, so the problem comes from the lambda function. That was not the correct function. Okay, now let's run. It gives us square 15. Okay, so the lambda function is correct. 2 sine 2 square root of x. Okay, now it's correct. By n, yes. Now the point that we use here is from 6. So do we have 11? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we did this manually, but we can also compute this. We can compute it using the linspace, right? We can use linspace to do this, right? But let us correct the program first, but we will change this also. I did this manually, but we can compute it in one line. So what I mean is that you can use this code. You can say x is equal to linspace plus lin. Then you take the interval a, b, n. How many subinterval do we need? Capital N. You see, so it should return exactly the same value, but we'll check that later on. Okay, I don't know, linspace maybe might be NP, eh? Okay, anyway, we'll check all those. So we initialize here, so we should check this for the odd. Oh, you see what we didn't do? In our formula, we didn't add the factors. Remember that in the formula, we have the factor 2h by 3, 4h by 3. We didn't do that. We didn't multiply. We need to multiply here. This final result, because here is the summation, but this final result, we multiply this by, for the odd is 2h. Oh, sorry. It's my fault. So I didn't add that formula. It's for odd, for even is 2h. 2h by 3. And now the other one is 4h by 3. 4h by 3. So you see, you should be very careful. It's because we did not add this. That now I hope so. You see, problem is interesting, eh? It's really interesting. So we didn't add these factors, so that's why we're having this last result. Now, if we enter, ooh, this is not witchcraft, guys. Hey. Oh, Kashupi. Oh, it's not witchcraft, no. You see, it's simple. Kashupi. This is not witchcraft.
Say it is witchcraft.
Yeah?
It is witchcraft.
Oh, Simon and Johannes, what do you say? It's not witchcraft, ne? That is the result. It is there. We have 8. We have 1 8. Yes. We have 3 0 is there. We have 1. Yes. We have 5 5. Right? Okay. So it's there. We have So we have all the results. So it's there. So we have even more digits here. Okay. So this is a simple programming. You see, it's just simple. You just apply basic rules. There's no witchcraft. You just apply the basic rule that you know. The loop, right? You use the loop. And then you look at the formula. You just look at the structure of the formula. And that is it. All right. Now, this one, I coded this manually. I told you. You saw it for yourself. So instead of doing this, just imagine that you had 50. You will not be coding that manually. Eh? You need a formula for that. So let's change that and use this one. Use that one. Let's see if it will give us the same result. If it doesn't give, it means that something is wrong with the linspace function. Right, okay. Now it gives 7. So it means that in this linspace, what did I do wrong? Linspace. It's as if there's less point to n. Yeah, because if you would take this, you would take b minus a and you would divide by 10. So that's exactly what I have here. Or maybe here we divide by 10 minus 1. Wait. So maybe let's see if I add plus 1 here. Okay, anyway, let's see. Something. Hey. All right. All right. Anyway, everything is fine. It's fine. So here you have n plus 1, right? Because in the formula, when you use the linspace here, the n that you put there, it will take that n minus 1. You take that n minus 1. But we want n itself, not minus 1. So that's why I added 1 here. Anyway, you just need to understand what linspace does, right? You need to understand what it does. Okay, so that is it. We have exactly the same result. Okay. I see that some of you don't want to leave, but I will stop here for today. It's so sweet that people don't want to leave. You need to program on your own. All right, guys. I hope you enjoy. I don't hope you really enjoy, because I can see you're still there. You don't even want to go. But please let me go. Okay, guys. God bless you. See you on Friday. Bye-bye. I see that you don't want to go.